This is Unit 1D. It deals with total internal reflection. So you recall from the last video that we've got two kinds of behavior that we're interested in here, refraction and reflection. They sound quite similar, and they are similar in some respects, but they are different as well. So we've got a change at a boundary. So here we've got our boundary between something that is not very dense and something that is denser. Now what happens depends on the angle at which the light comes in, and the critical angle effectively is the dividing line between these two behaviors. So this short dash here is coming in at an angle to the normal, which is this line here, which is less than the critical angle. So the light is coming through here and it's going through into the other medium here. So it's being deflected, it's changing direction as we said, but there's no reflection there. Now if we increase the angle beyond the critical angle into this green zone here, we get total internal reflection. So these longer dashes here are coming in and they're reflecting off this internal boundary as though it were a mirror. So we've got these two behaviors, both to do with light, but crucially they vary according to the angle here. Now it's the total internal reflection we're interested in, and we'll see how it's useful to us. So we're talking about energy, we're talking about electromagnetic waves, and we're talking about infrared and light in particular in an optical fiber. But before we get there, let's see the beginning of the story. Let's imagine we're sending a text and we're trying to send the letter J. Now your phone will turn that into a conventional number, 74 in this case, and it turns that into binary, which is just a different number system which involves ones and zeros. And it's a bit like Morse code, and your phone will send, using microwaves, a series of ones and zeros to its local mast here. Now at the local mast, this is turned into light, and this light is sent down an optical fiber. It's actually very small, obviously we're not showing it to scale here. Now it would be impossible to have a completely straight fiber between the two masts. It's got to go through all sorts of twists and turns, but that's not a problem because of total internal reflection. Providing the angle is right, providing the angle is beyond the critical angle, we're going to get total internal reflection, and it's going to bounce along this optical fiber till it gets to the mast where your friend's mobile is nearby. So again, it turns it into microwave signal. It sends off these ones and zeros. Your friend's phone will receive the ones and zeros, turns it back into a normal number, and then into a J, which is the beginning of a text. Let's have a look now at lasers in a little bit more detail. So as we said, we're still dealing with a form of energy, we're dealing with electromagnetic waves, and we're dealing with light in particular. So laser light is just a form of light. There's nothing really weird about it. It's just coherent light. Now this is quite a technical term, so let's spend a little bit of time on it. White light is a mixture of lots of different frequencies. I'm only showing 3 here, but a whole mix of frequencies, and your eye will, or rather your brain will understand that as white. Now we can have monochromatic light. So chroma means color, mono means one. Now we could achieve this by having a filter which would filter out the blue and the green, or we could shine it on an object which will absorb everything apart from red and it will reflect off. But as we can see here, the peaks and the troughs don't necessarily line up. So for that to be the case, they need to be in phase, or we describe that as being in phase. And if both these things are true, then we say light is coherent. It's impossible to have anything other than monochromatic light being coherent, because if it was blue and red, they could never line up. But these 3 little animations illustrate the idea, hopefully. So laser light is very useful to us. It's very intense, which means it can have a lot of energy per area, and it's very precise because it doesn't diverge very much, which makes it very useful for a number of applications. Most obvious one being surgery, laser eye surgery being an obvious example, but lots of other kinds of surgeries as well. It's an intense transfer of energy which can destroy unwanted tissue. It's used in CD players where we have these grooves and pits and the light bounces off and is received. Again, the intensity comes into play for cutting. We can concentrate a lot of energy, so something will melt or vaporize, and there are also military applications. So that's laser light.